Okay, guys, here we go. Today in class, we started talking about section 1.2, properties of functions. And we got through a good chunk of, let's say, the first couple pages here. So just kind of rehashing what we did, we defined the word function so that it's a relation that meets a certain condition where every x gets mapped with exactly one y. We talked about the vertical line test, which lets you know whether a graph is picturing a function or not. And then we kind of we talked a little bit about piecewise functions that end up with graphs that kind of look like this, where they have these different pieces to them. So they're called piecewise functions. But after that, we kind of, the plan was to get on with this concept of continuity, what it means to be a continuous function. And we had kind of a layman's definition, meaning not a very formal definition, just says it can be drawn without lifting the pencil off the paper. But then we got into the mathematical definition, and we realized we had to kind of talk about the idea of a limit. And a limit is generally an idea that's reserved for calculus, but it's something that we can, as we are on our way to calculus, may as well get used to now. And a limit, remember, is basically saying what's happening to the y values of function as x gets close to a particular number. So, we could even borrow this picture that we have right up here and say, from this picture, the limit as x approaches 0, so here's 0 right there, of our function would happen to be, well, what do you think it would be? Where are the y values of this curve heading as x gets close to 0? And you can see those arrows are pointing toward a y value of 1. So we could say the limit of that function as x approaches 0 is 1. So it just kind of is a descriptive tool. And what we wound up talking a lot about today is a limit might be heading toward a certain number. For example, as x gets close to 2 in this picture, our y values might be heading close to 3. So we could say, if this is a function f of x, we could say the limit as x approaches 2 of f of x is 3. But notice that f of 2 has no y value there. There's no spot that's filled in. So we would say maybe it's undefined. This function's undefined at 2. However, the statement that the limit as x approaches 2 of f of x is 3 is still valid. So where are you heading? You're heading toward a y value of 3. So I'll show this in red here. So we're coming up toward a y value. What is that y value? Well, it's 3. That's what this statement says. Notice that even though we're getting close to 3 as our x's get close to 2, the actual value of the function at the actual value of the function when x equals 2 is undefined. Those two things are not mutually exclusive. It means they don't have to, they can both be true at the same time. So this continuity thing is a little tricky because of this notation. So we're going to discuss it a little bit further on the next slide. So on this slide, we're going to talk just kind of generally about what it means, again, a little bit more about what it means to be continuous, but basically how a function cannot be continuous. In other words, when it has a break in it, what does it mean as far as the different types of breaks that we can go. So I want you to think about discontinuities kind of in two major types. You have your removable discontinuities. I'm just going to write removable. I don't know if there's an E in there. I don't think there is. And non-removable. Okay, so I'll just put non-remove. Removable discontinuities are exclusively going to just be holes in a graph. Okay, and we saw something like that today on the board. I might have written a graph that comes up like that, has this tiny infinitesimal hole, and then continues on. It's called a removable discontinuity. You don't really need to know why it's called removable discontinuity, but it's because functions like that generally happen with something where you might have something like x plus 1, x minus 2, and then in the bottom you have x minus 2. So clearly, if this is your function, if you try to put x equals 2 in there, you're going to cause a problem because your denominator is going to be 0 and your numerator is going to be 0. And 0 over 0 is not a number. Okay, so I'll put NaN, not a number. But what happens if you literally remove those factors of x minus 2? Now you have a perfectly harmless linear function of x plus 1. And now when you plug in 2, you get 2 plus 1, and you get 3. So this graph up here is a perfect example of what a removable discontinuity, what a function might be, and what its graph might be like. So in other words, in this function, the x plus 1 function, there would be no hole. You could literally plug the hole. Non-removable discontinuities, those are functions that are going to have major disruptions in their graphs. And as you can see over here on the slide, non-removables, two types are jump discontinuities and infinite discontinuities. A jump discontinuity is something like your function's cruising along and it comes up to a certain value and then it suddenly jumps up and goes somewhere from there. There's this major break between the 2 points. There's no one single point that we could fill in that's going to cover that break. The other type is what's called an infinite discontinuity, and that's when you might have, we have some examples of that over here, when you have a function that might be heading up toward positive infinity as x, say, gets close to 1, and then on the other side, it could be either heading up toward positive infinity or maybe heading down toward negative infinity, but that is again a major break in the graph. There's no one point that you can fill this gap with one guy heading up toward positive infinity and one guy heading toward negative infinity. And now our final thought on continuity. What it takes to be continuous at any given number. You know, I have in my notes here at x equals c. Well, c just represents some particular value. For example, we might, c might be 5 or something like that. F of c might be 2. So this would be the point 5 comma 2. All right. If this graph is going to be continuous at 5 comma 2 or at x equals 5, here's a couple things that have to happen for a graph to be continuous at any particular x value. And again, I'll just use 5 for my image here to kind of keep things consistent. So the first thing you better have, this first condition, is the function better be defined at 5. That means you better have a point there. Okay, big deal. So we have a point there, so it's certainly going to be defined. Now, statement 2, or condition 2, says the limit as x approaches c of the function exists. Now, c in our case is 5. So what we're saying is that as our function comes in toward 5, an x value of 5, it's got to agree that it's heading toward a particular y value. So let's say there's 1, 2, 3. So if we drew this thing, and I had a curve that's coming up here, and as x got close to 5, the y values were coming in and getting close to this number right there. And then from the right side, the number is slightly larger than 5. We have y values that are coming in and getting close to a certain value. So now we could say bullet 2 has been checked, because as we're coming in from the left and as we're coming in from the right, as we're coming in here and as we're coming in here, they agree, the left and the right sides agree that we're heading toward a y value. But here's the problem. This function that I just drawn is not continuous. It's pretty obvious. There's a break right at x equals 5. Well, what's wrong? Well, I've met standard 1, condition 1. I've got a y value there, right there. And I've met condition 2 that my limit exists. Yeah, my limit's coming in. Looks like my limit is 1. Well, look at condition 3. It says the limit that exists in bullet point 2 better be the same as the y value that exists in bullet point 1. And what that's going to do is make it so that, let's say that y value at 5 isn't 2. Take away that guy. But let's say the y value at 5 is the same as what the limit was. And now you can see we're going to have a nice smooth curve, because the y values were heading toward a y value of 1. And then when we actually got to 5, we got a y value of 1. That seems like a lot of work just to say that the graph doesn't have a break, but that's what it takes. Okay, that's what it takes to come up with a function to definitely be continuous at a particular value. So we're going to catch on in the next slide. That's going to kind of close the book on continuity, and the next slide is just going to be a few more properties of functions that we can talk about that are going to be ways that we can describe our different functions.